So coming to chemical properties, the very important chemical properties I will discuss with mechanisms, which are very important. The mechanism, the chemical properties, mechanism based. Overall, you will study in most of the chapters how to prepare other things. So that you will study in the derivatives. So only the mechanism based important ones will study in this chapter. Okay. So the first class of chemical properties will be oxidation. Generally, you have this is an aldehyde or ketone, like we take a ketone. Okay, there can be reaction due to these alkyl groups. Okay, reaction due to this carbonyl part or net oxidation of the compound or condensation reaction. I will not deal with condensation reaction here. We will deal in esters and all chapters. I will briefly talk about oxidation, reaction carbonyl group. Reaction with alkyl groups are similar to whatever you talk as reaction of alkenes and all. So not much emphasis on this. Condensation is an important part of this chapter, but we're discussing it in esters and acid derivatives and all those parts, especially acids and all. So not much into condensation. In fact, I will not touch this part in this chapter. Alkyl groups, it's same as alkenes, mainly reaction of the carbonyl part, and oxidation will be discussed with mechanisms. Okay, so first group which I will discuss is oxidation. First, using Tollens reagent. What is Tollens reagent? Ammonical AgNO3 solution. Ammonical AgNO3 solution. AgNO3 solution is Tollens reagent. How is Tollens reagent prepared? Use NH4OH and treat it with AgNO3. You get the Tollens reagent, and you wait till the precipitate of Ag2O is first formed and then it redissolves. So you treat NH4OH with AgNO3 and then you wait till you get a precipitate of Ag2O and then it dissolves into the solution. The reacting species is Ag+. So this gives silver mirror test. The Ag plus get reduced to Ag, forming a silverish mirror on the test tube. This is only for aldehydes. So this is a test for aldehydes. This gives a silver mirror on the glass of the test tube. Ammonical AgNO3 solution, Tollens reagent. Remember, this is very important because it gives silver mirror test. No reaction with ketones. So what happens? AgNO3 plus NH4OH plus RCHO will give rise to acid plus Ag. So basically this will be, the reacting agent is Ag plus, which will exist in this organometallic compound form. So this is nothing but it will exist in this form, and Tollens reagent is a mild oxidizing agent, so it oxidizes only aldehydes, not ketones. Tollens reagent, ammonical AgNO3 solution, silver mirror test. Most important parts of the conclusion. It oxidizes only aromatic and aliphatic aldehydes, no effect on carbon-carbon double bonds, ketones, etc. Next, remember, Tollens reagent can give positive test with alpha hydroxy ketones like fructose. Therefore, fructose also gives test by Tollens reagent. Alpha hydroxy ketones will give it terminal alkynes and formic acid. So, formic acid, terminal alkynes and alpha hydroxy ketones will also give Tollens test apart from general aldehydes. Next, Fehling solution. Fehling solution generally contains two parts, Fehling A and Fehling B. Fehling A will be copper sulfate solution, whereas your Fehling B will be an alkaline solution of sodium or potassium tartarate, which is called Rochelle salt. Okay, so Fehling A is CuSO4 solution, Fehling B is an alkaline solution of sodium and potassium tartarate, which is Rochelle salt. Not going into details of that. So this also gives your aldehydes. What is formed? So again, no reaction with ketones. So this is test for aldehydes. CuSO4, the presence of NaOH, and RCHO. Remember, the reactive species is Cu2+. The cupric ion, which is deep blue in color, becomes colorless, or generally deep blue in color forms the Cu plus salt, which is white in color or colorless. So therefore, this test is given by aldehydes. So again you will get RCO minus plus Cu plus water. This is Cu2 plus. Okay. Then Benedict's solution. Just like Fehling solution, we used CuSO4 and sodium potassium salt of tartaric acid. Here we will be using again our very old friend copper sulfate. So it's a solution of copper sulfate and another solution. So Benedict also has two parts. One is copper sulfate, another consists of sodium citrate in the presence of sodium carbonate. Okay. So this also, there is no reaction with ketones, and you get a reddish brown color precipitate when you treat with aldehydes. Benedict solution, reddish brown precipitate treated with aldehydes, no reaction with ketones. So in case of Fehling solution, the blue color disappears in presence of aldehydes. Okay, alkaline salt of sodium or potassium citrate with copper sulfate, and it also has no effect. The only thing that you have to know is, in case of Benedict's and Fehling solution, only aliphatic aldehydes are affected and no other effect on any other functional group in case of Fehling's and Benedict's solution. Okay, and these are also used for test for sugar, for diabetes and all, Benedict's and Fehling's solution. So that's it. Now few other oxidation reactions I will tell. You know, if you treat it with alkaline KMnO4 or acidified KMnO4 or acidified K2Cr2O7 or even concentrated nitric acid, any aldehydes or ketones will directly get your acids, that is carboxylic acids as the products. Okay. So basically you will get carboxylic acid as the products if you treat with strong oxidizing agents like acidified KMnO4, alkaline KMnO4, acidified K2Cr2O7 or concentrated nitric acid, you will get the corresponding acid with same number of carbons. So another important reaction which I will treat is another oxidation, that is by organic peroxides. So Tollens reagent, silver mirror test, Fehring solution, Fehring solution very important. Organic peroxide, this is called Bayer Villager oxidation. What happens? You take an aldehyde or a ketone, treat it with organic paracids. This is an organic paracid. And what will you get if you take an aldehyde? You will get a corresponding, let me write it R dash for understanding purpose, and you will get okay. If you take an aldehyde, you will get a corresponding carboxylic acid. If you take a ketone, you will get the corresponding ester by Bayer-Villager oxidation. By Bayer-Villager oxidation, if you use a aldehyde, you get an acid. If you use ketone, you get an ester. This is the peracid as the reagent. What an example of peracid? Per-monosulfuric acid, per-benzoic acid. This is per-benzoic acid. Per-acetic acid or per-trifluoroacetic acid. If you take cyclic ketones, and I am treating per-trifluoroacetic acetic acid, okay. What happens? Ketones if you take cyclic ketones, then you have to treat with CF3, remember, and with this per-trifluoroacid, per-trifluoroacetic acid, what you get is the cyclic ketones undergo ring expansion to give rise to lactones. Okay, this is a lactone, cyclic ketones, ring expands to lactone in the presence of per-trifluoroacid. Okay, so what are the solvents that you use? The solvents that you use is chloroform and glacial acetic acid is the solvent in this reaction. Now let me discuss the mechanism and then we'll end oxidation reactions. This is Bayer-Villager oxidation. First, you can take an aldehyde or ketone, is the same. First, protonation of the peracid. Peracid releases the hydrogen atom. So this, then this is the per acid, this adds R dash, so this is minus, this is plus, so these are actually positive charges, so you get O, C double bond O, R double prime. Now this is the slow step of the reaction. The slow step, you lose this one, R double bond C O, so you are left with R C O H R prime O plus. Concerted mechanism in this state, this shifts, so you get R C O H O R dash shifts, concerted mechanism, so positive charge comes here, and then removal of this hydrogen atom, you get your ester. So of R dash, if you use H, you will get your corresponding carboxylic acids. Now some points. The first step is catalyzed by acid. Okay. Electron releasing groups in ketones and electron withdrawing groups in per acids accelerate the reaction. So the reaction is accelerated by electron donating or releasing groups in ketone and electron withdrawing or pulling groups in per acids catalyzes this reaction. Trifluoroacetic acid, if you use, which I used in the previous one for cyclic ketone, is a very good leaving group, so that facilitates the slow step. So in the slow step, you have this group being leaving, so the greater the ability of the leaving group, the greater the ability of the group to leave the compound, faster will be the reaction. So if you use trifluoroacetic acid, it's a better leaving group, so the reaction is facilitated. And remember, the oxygen of the carbonyl group is always present in the carbonyl part of the ester. So the oxygen in the carbonyl group, suppose if I make it O18, this oxygen in the carbonyl group is always present in the carbonyl part of the ester. It doesn't go with this part. Okay? Let me tell you what forms the basis for the chemical properties. So let's talk about nucleophilic addition. So this is your carbonyl group. So plus delta charge on oxygen, plus delta charge on carbon, minus delta charge on oxygen. So your nucleophile comes and attacks the carbon atom. Okay, so this double bond gets shifted here, means the lone pair of electrons get shifted here. So this gets actually positive charge. Then your H plus ion comes and goes and attaches here. So let's take an schematic diagram. So this is plus delta, this is minus delta. Plus you have nucleophile, which is very strong nucleophile, let's take. And then in the slow step, this tetrahedral compound is formed, the nucleophile with it, and then when you add water, it forms R, COH, H, Nu. Now let's talk about the reactivity. That is reactivity of the carbonyl group towards the nucleophile. So to basically see, there in organic chemistry there is nothing that which follows every single play, but we can generalize where it follows in most of the cases. There always exist exceptions. So, and wherever it exists, it will be mentioned. So basically reactivity is directly proportional to the electron deficiency of the carbonyl compound. So the reactivity is always proportional to the electron efficiency of the carbon. So, as the delta positive charge on the carbon containing the carbonyl group keeps on increasing, what happens? It's the tendency for the strong nucleophile to get attached to it also increases. The nucleophile always looks to the place where it can donate its electron easily, and carbon is wanting that to take the electrons. So carbon is wanting electrons, nucleophile wants to donate electrons, good pair, good bonding forms the compound. And the problem is reactivity is seen to be inversely proportional to steric hindrance. What happens now when the nucleophile is coming to attack this carbon? If these groups are very hindered and all, they're surrounded, then how will the nucleophile enter? It has to fight against the compound, the groups, and then enter, and it causes a lot of energy criteria and all. Therefore, when there is a steric hindrance, the reactivity is generally not very high. Now when we have a reaction, what we have to decide is the reactivity, and that reactivity depends on these two factors. Now in a particular reaction we have to see which factor compensates for the other, or which factor is a major contributing factor. Generally this is a major contributing factor unless you are very highly steric hindered. Okay. So these are the hand tip rules. Let me discuss something about this then, so that you understand with much more details. So when we talk of inductive effect, because generally inductive effect governs this principle, so we see if F is attached, it's more than chlorine, more than bromine, more than iodine. This is what I am talking is reactivity. Okay. Similarly, if I have CH2X, CHO, this is less than CH, X2, CHO, this is less than CH, X3, CHO. See, here the halogens atom as such do not cause much of hindrance to the atom, to the compound. So what matters the most is the halogen groups, because they being electron withdrawing groups make the carbonyl compound a very electron deficient at the carbonyl compound. At the carbonyl location of the carbonyl compound. Okay. Similarly, if you have H, C double bond, OH, this is formaldehyde, and so on. Okay, what happens here? This is an example of stearic. So here, this is more reactive. Here, this is a plus I group, so increase the density. Okay, but normally it's seen that this increases more than this. Okay, and Here it's directly connected to further increasement. Here 2 R groups, more further increasement, ketone. Now you see, as this is going, it's becoming more sterically hindered. Because of the steric hindered case, the reactivity decreases. Therefore, ketones are much more less reactive compared to our aldehydes. So aldehydes are more reactive than ketones. Here the steric hindered effect comes into existence, where here among the ketones and among the aldehydes also the steric hindrance effect and the electrophilic position also affect. See, if you consider this aldehydes, or suppose this aldehydes is the electrophilic position that's affecting. But as you go this side, is the steric effect which is coming into it's coming into our consideration compared to electrophilic effect. For example, you see this is looking to be more than this, but here when you have 2 attached, obviously it should be more from inductive also, but here the steric is the major concern. Okay, so generally therefore ketones are not very good agents, or it doesn't react much compared to aldehydes. So you require, even for oxidation and all, you require very high affinity oxidizing agent. That's been very strong oxidizing agents. So I told you, let me discuss some reactions of alkyl groups. Okay, so reactions of alkyl groups. Some points: acid catalyst, halogenation, remember, I'm not discussing one more important reaction of this chapter, which is the halophone reaction. Okay, so we have the halophone reaction and basically the hydrophone reaction, which is a test of carbonyl compounds. Okay, and in which hydrophone is formed and the yellow precipitate and all. That part will be either discussed in the previous chapter or in the next chapter, depending upon where it's most convenient to be used. Okay, and halophone reaction should be was partly discussed in alcohols chapter also, about the formation of halophone. But that is one more reaction. So I told I'll not be going into great depth of the reactions of the alkyl group, but I'm just mentioning some brief key features of this part. So as you are seeing, that acid catalyst halogenation will give only monohalo derivatives, whereas if you have base catalyst, that means you have only one derivative, monohalo. Therefore, if reaction like hydrophone, where all the 3 alpha hydrogens are replaced by iodine, okay, or any hydrophone or halophone, those are generally base catalyst. So base catalyst halogenation, what happens is, it goes on replacing all the similar alpha hydrogen atoms. Okay, so base catalyst halogenation has the ability to replace all the alpha halogen atoms. That means as you increase the quantity, that first step happens, then second step, third step, second step 2 hydrogens replaced, third step 3, 4, and all the possible similar alpha hydrogen atoms are replaced in base catalyst halogenation. Okay, so that was little bit of halogenation. So let me take an example. What is this? Acetaldehyde. You take with chlorine, and let me take acid catalyst, that is acetic acid. You get CH2, Cl, CHO. Whereas, suppose, let me take, what is this? Acetone, and I take Cl2 and I use some base, let's say OH minus, okay, See, chlorine should be available in abundance. What happens in this case? You get CH3, C double bond O, C, Cl3. So you see all the similar alpha hydrogen atoms here are replaced. That means once it starts replacing here, second time also it will replace here, third time also it will replace, fourth time also it will go on replacing there. Because once one chlorine is getting attached, its affinity to take is increased, and so the chlorines go on adding here till all the hydrogen atoms of the same nature originally gets replaced. Not that this one, it doesn't have CH2Cl, CH2Cl, then Cl, not like that, but the same type in before. Or suppose you see this one, all these three will be replaced. Then it goes for that side. Okay. Generally, the reaction doesn't proceed so further. It goes to the next step. Means it starts reacting with the next compound. Okay. When the availability is less, then it may go for such things. Next is by SeO2. So alpha CH2 group will get converted to ketone, whereas alpha CH3 group will get converted to aldehyde. Remember, this is the steps for CO2. Suppose I have a ketone. This is alpha CH2 group, SeO2, it gets converted to ketone, whereas this alpha CH3 group, it gets converted to aldehyde, C double bond OH, C double bond OH, plus this will oxidize, so this should get reduced, and plus water is eliminated. So the order of reactivity, methyl greater than CH2 group greater than CH group. Okay, I hope it's clear. One more is deuterium exchange. That is, suppose we have this. See, this is alpha acidic carbon. So if you treat with D2O in presence of a base, which are C double bond O, CD2 R, because in the solution, this being the alpha carbon hydrogen atom, suppose in the presence of the base, if this is removed, this is very stable because of resonance, and what happens, it picks up a deuterium from the picks up a deuterium from the solution and forms that. So generally this active methylene compound forms this by deuterium exchange. Okay. So if in a ketone, if you have alpha chiral carbon, it undergoes racemization. Earlier generally it may not happen because you have 2H on it. Okay. But in case of ketone, if you have an alpha carbon atom, so when this H is removed, okay, if you have an alpha chiral carbon, when this H is removed, so it is having a H, suppose, because the alpha atom will have a H, obviously. You remove the H, so it becomes planar, right? Then when it becomes planar, the tetrahedral shape becomes planar, and then it may pick up hydrogen atom from the solution, either coming from this side or coming from the back. Since it can pick up in any direction, therefore a racemic mixture is formed. So ketones having active alpha chiral carbon generally exist as a racemic mixture in solution. Okay. That's the principle of deuterium exchange also. So those are the main points. Now apart from that, you have one more thing, that is alkylation. That means the alkyl groups can be further alkylated in this process. So the alkyl groups, let me tell you in great detail. So let's take this compound. Okay, so let's take this particular compound. So in this particular compound, you have two alpha carbons. Both of them have hydrogen. So let's take this and this. Now if you treat it with base, generally alkylation takes place in presence of a base. And if you take a base, suppose NaH, this is a very small base, as you can see. So NaH is basically a very small base. So when you take NaH, it's a very small base. So in presence of the small base, this can easily go pick up this hydrogen, and therefore this forms a minus sign. Okay, right? I hope it's visible. Now what you do when this hydrogen is removed, right? So negative charge comes here. Now you treat it with CH3I or any methylating agent, any alkyl halide. You can treat it with C2H5I, whatever, XYZ. Then what happens? This is positive, right? Here, and this is negative. I hope it's clear. This is positive and this is negative. So this positive part goes attached here, so I minus goes out, and generally as NaH, this H minus comes and picks this, and so basically after that Na plus is present, what you call beaker, I minus is present, Na is formed. So that is anyway not relevant for us, but this is what is mainly formed. Whereas if you use a very bulky base, like if you use a very bulky base like lithium diisopropyl amide, so a very bulky base, lithium diisopropyl. You know isopropyl is very good group. I mean very big group. So you have two isopropyl and amide. Lithium diisopropyl amide. It's a very bulky base. So suppose this compound has to come here. Okay. Suppose this base has to come and pick up an hydrogen from here. It's a huge bulky base, right? So when it comes here, these two methyl groups provides a resistance to it. So this is the steric effect. Because of this particular steric effect which is present, you know the reactivity changes. So because of steric effect, the reactivity decreases. So it can't come and pick up this because of this steric effect being present here. So it simply goes and picks up a hydrogen atom from this alpha carbon. Then if you treat it with any methylating agent, let me see CH3I. So what will you get? You will get CH2, CH3, C double bond O, CH, CH3, CH3. That's it. So here you see this is a center of series reaction taken. Okay. Now the point is, this is the kinetic product form, because it's formed quickly. Because see, when NaH has to come here, this is very free, right? It has to come here, pick up this and go. But if you see, this is more stable product. So this is the thermodynamic product form, because it's formed from the most stable carbon anion Okay, see this is more stable over here, and no, basically the most stable product is called thermodynamic product and the thermodynamic condition, and the fastest product or the least stable product is the kinetic product. So here is the kinetic product. It forms fast because remember this is easy and it goes and forms fast, whereas here you have this active methyl group where you can go and pick up and reaction becomes simpler, right? So basically this is the thermodynamic product, and let me check one more reaction. Now you should remember that carbonyl compounds always react better than alkynes in the case of this acidic hydrogen removal. Alkylation, or basically the acidity of this alpha hydrogen. So acidity of this alpha hydrogen is better compared to this. So if you see, in fact this alpha hydrogen acidity is better because this carbocation, this carbanion, I am making it more clear, this carbanion is more stable, okay, and quickly form product, but the product as such that is more stable than this. So that is thermodynamic product, this is kinetic product, and so depending upon the acidity of hydrogen, this is formed. Now you see in this case, this is carbonyl compounds, acidity is always better than your alkynes. So let me see one more. Let us talk about regio selectivity. This is regio selectivity because a particular region is being selected according to the base. So regio selectivity. So if I have this base and if I treat with NaH as the base, this is removed. So this is basically the thermodynamic products intermediate, right? But this is not very stable carbanion, but the product form is much more stable. So the fastest one that is formed is kinetic, whereas if you use LDA, okay, it can't come here, resistance and all. So here it goes. So this is the kinetic product. It forms fastest from the most stable carbanion. Okay. So that was about reaction of alkyl groups. Once more I am repeating, kinetic product is the one which is quickly formed from the most stable intermediate, therefore it is formed quickly, whereas thermodynamic product is the product other than kinetic product. In some cases, it is proven that the thermodynamic product is more stable. I am not talking about the intermediate, the product is more stable, whereas generally the product other than the kinetic product is stated as the thermodynamic product. That is the product which is not formed from the most stable carbanion or carbocation or reaction intermediate, which can be carbene. There are various reaction intermediates, okay? So kinetic is the fastest product because of the most stable carbanion or carbocation.